This is our second video for this unit, and this video will cover orbital shapes and some energies for polyelectronic atoms. Our objective for this video is to really get us ready to analyze electron configurations and start talking about some of the properties and periodic trends of the atoms. As we discussed last year, the s sublevel includes one orbital that is spherical. When the s sublevels for each energy level begin to overlap, the probability of an electron being located in between those sublevels are separated by what we call a node. This node is actually a gap between the energy levels where an electron has zero probability of existing. So you can see in our diagram here, we have energy levels 1, 2, and 3, and the s levels for each of those energy levels overlapping. And as the number of nodes increase, n increases, and n is our energy level. The number of nodes that we can ever find in between these s sublevels is n minus 1. The p sublevel has 3 orbitals each. P orbitals each have 2 lobes, and they are separated by a node at the nucleus. In fact, we've often described them as being barbell-shaped. The p orbitals are labeled according to the axes in which they lie using the x, y, z coordinate system. P orbitals also overlap when we start adding energy levels. P orbitals have nodes as the p orbitals for each energy level start to overlap. And again, we find this gap where the probability of an electron located there drops to 0. The d sublevel has 5 individual orbitals in it. The 5d orbitals first occur in energy level 3. They have 2 fundamental shapes. 4 of the orbitals are similar, and they have 4 lobes centered in the plane indicated by the orbital label as a subscript. For instance, d x squared y squared lies along the x and y axis, and the dxy lie between the axes. The 5th orbital, dz squared, has a unique shape, and with 2 lobes along the z-axis, and then a belt-shaped portion of it that is centered on the xy plane. So as you can see from this diagram, most of the d orbitals lie diagonally between the planes, with the one exception with the x squared y squared, and then you can also see the 5th orbital in this group that has a different shape altogether than the others. The f sublevel has 7 orbitals in it, and we first see f orbitals occurring in energy level 4, and they have shapes that are far more complex than any of the d orbitals. These orbitals are not involved in bonding in any of the compounds that we're going to look at. As you can see, each of these orbitals have several lobes, and not all the shapes are the same. When we start talking about sublevels, we often have to include energy levels and orbital energies. We're first going to talk about the hydrogen atom since it's more simplified. For the hydrogen atom, the energy of any particular orbital is determined by the value of n, our principal quantum number. Thus, all orbitals with the same value of n have the same energy. Now, this is not the same as any of the other atoms, but because hydrogen only has 1 electron, their energy levels are the same. So what I'm saying here is the s sublevel, the p sublevel, the d sublevel, all of them are said to be degenerate because there is no hierarchy in energy levels between them. But again, this is only for the hydrogen atom because it only has 1 electron. So each energy level has sublevels that are equal in energy. But this is not the case when we have something that's called a polyelectronic atom. Polyelectronic atoms are everything but hydrogen. This is an atom that has more than 1 electron. Poly means many, therefore these are atoms with many electrons. To look at these polyelectronic atoms, 3 energy contributions must be considered. 1. Kinetic energy of the electrons as they move around the nucleus. 2. The potential energy of the attraction between the nucleus and the electrons. And 3. The potential energy of repulsions between the electrons. So these are all three forces and interactions that are going on all at the same time in any polyelectronic atom. In addition to having these forces, we don't know the electron pathways. So dealing with the repulsions between the electrons can't really be calculated exactly. And this is what we call the electron correlation problem. The electron correlation problem occurs with all polyelectronic atoms. To deal with this, we assume that each electron is moving in a field of charge that is the net result of the nuclear attraction and the average repulsions of all other electrons. So what does this mean? In other words, a valence electron is attracted to the highly charged nucleus and is still repelled by the other inner core electrons. The net effect is that the electron is not bound nearly as tightly to the nucleus as it would be if it were alone. This is the screening, or what we have called the shielded effect. Because of this shielding effect, orbitals within a principal energy level do not have the same energy. They are not degenerate. Sublevels vary in energy within the principal level. S is lower than P, is lower than D, is lower than F. So if you look at these two energy level hierarchies, you can see hydrogen on the left, and you can see where all of the sublevels are degenerate. And then if you look at the polyelectronic side, you can see where we see the differences, where there's some staggering between the sublevels. However, the polyelectronic atom sublevels are staggering because of these conflicting interactions between the electrons and the attraction of the electrons for the nucleus. But we will see this effect in the filling order of our electrons as we move forward into electron configurations in this unit. But this is all I'm going to cover for our second video, and we'll start electronic configurations tomorrow.